Hello and welcome to Electronica Sovietica. Today we're going to look at the MT1804 Microtrainer, originally produced in 1984 in the Soviet Union. However, my model, I happen to know, was produced in 1986, or at least that's when it received its guarantee, which is handwritten in the manual you can see. I also have reason to believe that this device was untouched until I bought it in 2019, as when I got it, the device itself was wrapped in large sheet of plastic, which had not been opened, and the manual was certainly never opened, as it was shrink wrapped in plastic, which I had to cut open to get at. The MT1804 is a functional replica of the Advanced Micro Devices AM2900 Learning and Evaluation Kit. Although, as far as I can tell, it has some significant differences. One is that, as far as I can see, it was not produced as a kit, but it was factory produced. And secondly, while on the internet there are many complaints about the AM2900 that it was made from cheap materials, the MT1804, I believe, is made from rather good materials and has rather a lot of gold in it, as it says in the manual. This fact might also explain why it's quite hard to find a working model, because unfortunately much Soviet electronics has long since been cannibalized for the gold content. Now, I'm not a computer scientist, but I have done my best to understand how this machine works. Essentially, it has 16 32-bit words which the user can manipulate using the front switches on the machine. And these words act as instructions to the processor. However, they act rather differently from the only analogy I have, which is 8080 and Z80 machine language, insofar as there are not separate instructions which can more or less be freely combined, but the words themselves contain a series of information which is then interpreted as an overall instruction. This is called bit slicing, and again, a computer scientist will explain to you better what that means, but essentially, as I understand it, what it means is that the 32 bits are divided into these slices, if you like, and they each do a different thing. So, for example, the first 4 bits, which are labelled here D1 to D0 to D3, are data bits. So this is where you can enter data that will then be manipulated by the rest of the instruction. These next set of 4 bits are sort of symbolic references to registers within the computer. So if you set, for example, B to 0, then if B is referred to elsewhere here, then the information will be either taken from or put into register 0. Then this is the arithmetic logical unit operator, and it has a very limited range of instructions here, all based on Boolean logic of various kinds. The one that I've seen the most of at the moment is this RVS, which is R logical ORed with S, which is often used to essentially assign variables values. I actually don't know what this C0 is yet. I'll skip this one. This one here, the operands, are then what's being seen as S and R in these instructions. And then these two MS ones are how to deal with shifts, which is rather complicated, and I'll get to in another video. And these bits here, 20 to 22, determine where the output of this operation goes. Yes, so does it go back to B, or does it go somewhere else? And finally, these last 2 columns here, these instructions will say different jumps that can be done, either go to the next line or go to something specific that's required by the user. And I say line, memory address, and here is the actual memory address you would put for some of those operations to work on. And This may seem rather abstract, so the next thing I'd like to do is actually show it in operation on the machine. So now I have the MT1804 connected to 5 volts from a desktop computer, and it will now accept instructions. We will look at this simple program, which is to cause a shift in data to the left, which we can then view. One thing you may notice is that not all of those columns I talked about, all of those, as I call them, slices, I'm not sure if that's correct, but those fields, I think is the correct term for them. The fields I talked about are not complete. The reason for this is rather simple, that, for example, in the first command on line 0, A is not referred to anywhere else in the command, so it's not necessary to set A. It makes no difference what we set it to. The other thing is that the 6th and 7th columns are not used because there is no jumping to different addresses, because we will do that manually, as we will see. It is actually possible to automate this program by adding data there, as I have done, but for now we'll just use the one in the book. So to set data, we have to use the front switches. So I'll just translate them, what it says here in Russian. So here it says load, here it says work, here it says run, here it says address, here it says data, and here it says multiplexer, and here it also says load. So this is a mode, load versus work, and this is load, which will actually load data into the memory. So in fact, by pulling that, I just loaded 0 into the first field of the first line there. There are actually 2 other switches here. This one is to go from step mode to automatic mode, and this one is to go from external to internal. I have worked with step and automatic. Internal and external I have not done. Again, I'm not a computer scientist, and I'm going to have to learn a lot more before I can probably do the external functions here. So, before we begin programming, I just want to say what this program actually does. So, as I said before, D is data. So here we're entering the number 2 as data into the instruction. B means we're setting B in the rest of the instruction to refer to the 0th register. Here, this I mentioned before is R logical OR S. So it's going to take whatever it gets told to take for R and S and do logical OR with it. In fact, what it's going to get for R, if I'm not mistaken, is D, and for S it gets 0. It may be the other way around, it doesn't make any difference, because logical ORing anything with 0 will give itself. So basically, this is a way of assigning this number into another register, because this then puts the result of the operation into the register referenced by B, which is register 0. Now, the next line, it doesn't care what data is coming in because there's no data coming in anymore. It's still referring, B still refers to register 0. The operation is actually still this R logical V S, but this time R and S are defined differently, in that this time I believe R is 0 and S is B. So now we're doing logical OR on B, so it's setting it to itself. However, when it then exits, it actually gets doubled. And this is what's going to cause the shift. So, and then you'll also notice that these 2 bits are set. The 2, I can't remember what they're called, but MS, I believe, bits. And this combination refers to a certain kind of shift. And honestly, I haven't yet got my head around it. Long story short, this program should put binary 2 into register 0 That's what the first line does. And in the second line, it should double that number, thereby causing a left shift. And this setting the shift as it is set there, what I do understand is it will then just cycle. It won't go off the end, it will just cycle round. So that's what we should see when we run the program. So now let's get on to the actual programming. As you can see, in the 0 field, we need to put the number 2, yes? Binary 0010. So to do that, we first of all make sure the address is set to 0, which is what we want. We also have to make sure the multiplexer is set to 0, as this means the 0th field, the least significant field. And then we set our data to 2. And then we pull the load lever like this. And you'll see that in the top, the memory, that says memory in Russian, now contains the number 2, which is what we want. And we can continue to do this to complete the rest of the command. I'll do a couple more, and then I'll do the rest off camera. So now we want to go to the first field here, and it needs to contain 0. So we will set the data to 0, and we will pull the load lever, and we will check that indeed the memory now contains 0, and so on and so on. So we just we don't need to put anything into 2. It doesn't matter what's it. Oops, I just pulled the load lever again. It doesn't matter. It's right. We don't need to put anything in 2 because there's nothing in column 2. In column 3, for the arithmetic logical unit, we need to put 0, 1, 1. We need to have the value of 3. So we set our data levers to 3, and we pull the load, and we have a look, and we see, yes, so that memory address now contains 3. And we can actually cycle back to check we've programmed things correctly, right? We can go back to 0. We can see we've got our 2 there. We can go to 1. We've got our 0 there. We can go to 2. We don't care what's there because we're not using A. And we can go to 3, and we can see that our number 3 is in the memory there. So that's how it goes. Using the multiplexer, you can go right up to column 7, to field 7, and you can enter all the data using these 4 bits here, and then by pulling the load lever. I hope that's clear. I will now complete the other 2 lines of program and come back to you. Okay, so now we have the program set up, and we're going to run it. In fact, we're not going to put this into work mode because we don't have jump addresses set up properly. We're just going to do it manually. The other thing is I've already set the multiplexer to 1 here because we want to see, as we run the program, we want to see what the ALU is producing up here. And to do that, we set the multiplexer to 1. It's like a kind of monitor function. You can monitor different parts of the system, and we want to see what the ALU is doing. So we have this is set to 0, everything's set to 0, and we're going to pull the run lever, and we hope to see binary 2 appear up there. And it does. Now we're going to manually switch to address 1, and we're going to pull the lever again, and what we hope to see is it shifts to the left as it doubles. It didn't do it. There is something a bit cranky about this. Sometimes it needs a second pull. And there it's going now. Okay, and as you can see, now it is happily rotating to the left. Why it didn't work the first time, I do not know. Perhaps I've not fully understood. Perhaps it's not exiting the ALU until the next cycle. I don't know. But as you can see, now it is doing what we hope, and it is rotating, and it is also cycling to the left. So that's all for today. Thank you everyone for watching. I hope you liked it. If you did, please like and subscribe. If you know why the program didn't act as I expected it to when I ran the second line, I'd also like to know. And let me know what you'd like to see in the future with this machine. And I have other machines as well, which I will present. Also, as my knowledge gets better, I may do a more technical overview of this machine.